Let's now understand the properties of magnetic materials that make them to be able to be magnetized or not. We are going to get into the domain theory, where we are going to notice that all magnetic materials are made of regions known as domains. These domains contain dipoles, and the dipoles are the ones that are responsible for magnetization or demagnetization of a given material. So magnetic materials contain small magnetic regions. So we have sections in any magnetic material that makes it to be either magnetized or demagnetized. These sections or regions are called domains. So all the domains are characterized in such a way they are able to be magnetized or not. Now, domains have small magnets known as dipoles. So there are very tiny magnets known as dipoles in those domains. So each domain has a dipole, and each dipole, as we are going to notice, has a north and a south. So each small dipole has a north and a south, and therefore you notice that those dipoles are going to determine the end which is going to be a north and the end which is going to be a south. Now, dipoles are arranged in a given domain as follows. So as you can see in our diagram here, we have a domain. So this is a dipole in a domain. The whole of this is a domain. We have a line just intersecting the axis. The axis intersecting the whole domain is known as the magnetic axis. Now, each dipole here has a south and a north, south and a north, south and a north, and so on. So each of those domains has dipoles, and each dipole has a south and a north. And therefore, the dipoles are the ones that are responsible for the determination of the end that is going to be a south and the end that is going to be a north. Well, now let's know how the magnetic and non-magnetic materials are in terms of the domain theory. Now, we have an unmagnetized material. So we have a material that is, of course, can be magnetized, and its dipoles are arranged randomly. They do not face in the same direction. So we have dipoles that are facing different directions, and of course, if you want to magnetize unmagnetized material, then you're going to introduce a magnetizing field. If you introduce a magnetizing field moving to this direction, then we are going to have all the domains or all the dipoles facing in the same direction. So therefore it means this material here is a magnetized material. Now, we have the term here known as saturation. So what is saturation? Now, if you are magnetizing a given material and all the dipoles have arranged themselves to the end, you are trying to magnetize a given material, and all the dipoles have already arranged themselves in a given direction. They will not be rearranged any further. Then we are going to say that point is a saturation point. They have reached a saturation point. No further alignment that is going to happen. Now, we also have hard and soft magnetic materials. Now, hard magnetic materials are hard to magnetize. That's what we say. The dipoles and the dipoles of the hard magnetic materials are very hard to align. Now, if you're using, as you are going to see these methods here, as you use, say, induction method, you are trying to induce the a magnetic field to a given material. The domains or the dipoles there might prove hard to be aligned properly, and therefore such materials are called hard magnetic materials. It's good to note that at the end of the day, hard magnetic materials can be magnetized, but it's going to really take some time to magnetize such materials. Now, we have soft magnetic materials, and soft magnetic materials are those materials that are easy to magnetize. Their dipoles are easy to align. So if you try to even induce some magnetic field, it means they are going to be aligned easily. And of course, it's good to note that hard magnetic materials are hard to magnetize, but the moment you have magnetized them, it is hard to also demagnetize them. So also, again, just like hard magnetic materials, if you can be able to magnetize a soft magnetic material faster, it means then it's easy to also demagnetize a soft magnetic material. Now let's get to a magnetization of magnetic materials. How do we magnetize magnetic materials? We have so many ways in which we can magnetize these materials. Now we are going to explain each one of them, but for now let's highlight. Now we have the first method known as induction. Induction simply is inducing magnetic field through an magnetized material. So if you use a magnetized material to induce means bringing closer or just touching the magnetic material with an object or with a material that you want to magnetize, it's going to be magnetized. Now stroking, it means you're going to rub over, you're going to stroke. You can rub a given material that is unmagnetized with a magnet, and therefore it means you're going to try and align those dipoles, be magnetized or to face in one direction. Also we have hammering. So we can use hammering. We can hammer a given unmagnetized material facing a given direction, of course north south, as we are going to see, and if you hammer the material, it is going to be magnetized. Now we also have electrical method. Now at the beginning of this topic, we explained that this topic deals with electricity and magnetism. Electricity, if you can introduce electricity to a given material and magnetized using a solenoid. So we use a solenoid, connect power, then we have current flowing in a given direction. We can be able to magnetize a given material using the electrical method. So let's get to each one of these and explain how we can do magnetization of these materials. So let's go through each of these methods of magnetizing magnetic materials. Now, induction method. How do we magnetize a material using the induction method? As you can see here, we have a magnet with a north and a south, and then we have some small pins. Small pins. These are pin and these are pin. Now, the pins are going to be induced with the magnetic field, and therefore the dipoles of those pins are going to align towards one direction. It means therefore those pins will have been magnetized using the induction method. Now, one thing to note is that the pins repel each other. Why do they repel each other? So as you can see, the pins are repelling each other. The reason is because in the induction method, the point where it is in contact with a magnet acquires an opposite polarity. For example, this is a south, and then the pin of this side is going to acquire a north. And therefore, if it is the north, we said in the properties of magnetic materials or the properties of magnets, if one end is a north, then definitely the other side is going to be a south. And therefore, this is a north, we have a south here, then this is a south, the pin acquires the opposite polarity, which is north, and therefore the other side of the pin is going to be a south. And therefore, if you bring the pins closer together, you will know they are going to repel because the ends of the pin have the same polarities, that is a south and a south. That would happen if the pins were induced from this end. If this is a pin, another pin, so this one will acquire a south and a north on this side, a south and a north on this side. And of course, they are going to repel each other because they have the same polarity from the basic law of magnetism. The second method that we are going to discuss here is known as the stroking method. So, stroking means we are going to rub a magnet or a magnetic material using a magnet. And we have two methods, or we are dividing the stroking method into two. We have single stroke, where we are going to use a single magnet to stroke a given material so that we can it can acquire some polarity. So we have a bar here, AB, and we want to magnetize it. So for us to magnetize using the stroking method, we are going to stroke the bar using the magnet in this way. So we're going to rub over, and then we take in this direction, then come back, again rub, again rub. What you're doing therefore, you are trying to align the dipoles. Remember the dipoles here. this unmagnetized bar are arranged randomly, and therefore we want to align them using stroking method by making sure that they are magnetized or they reach saturation point. And therefore, as we try to align these dipoles in here, they are going to align until they reach saturation, and by the end of the day, this bar will have been magnetized. Now, one thing to note is that at the end here, this bar is going to acquire an opposite polarity from this one, and therefore this is a north, this is going to be a south, definitely. And therefore it means if you remove this one, if you remove this magnet here, you're going to remain with a north here. Now it's worth noting that at the end of the magnet, that is where we have the bar acquiring some polarity, and that polarity has to be the polarity that is opposite as this magnet here. All right, so let's talk about double stroking. Now, in double stroking, we are using two magnets. So these are one magnet and another magnet. The polarities are opposite. This one is south, north, south, north. And therefore, we want to make sure that this end is a given polarity that we want. And of course, it's going to be a south because this is a north. Because we have said here in single stroke, at the end of the bar, we have the bar acquiring the opposite polarity, and therefore it means as we try to align these dipoles using the double stroke method, so we are going to move them, as you can see the direction, stroke, we stroke so many times. At the end of the day, this end is going to be a north, and this end is going to acquire opposite polarity, which is a south. What we are doing in stroking, we are trying to trigger the dipoles to realign themselves towards one direction. So as we double stroke and the magnetic path is as shown in this diagram, then it means we are going to have them align towards one direction. Until they reach a saturation point, we will have magnetized the bar. Well, let's now talk about hammering method. Now, hammering method. So hammering method is simply we are trying to hammer a magnetic material so that the dipoles can rearrange themselves or to be in one direction. Now, before you hammer, you have to make sure that the bar is facing the north-south direction. This should be a south. The north-south direction. The north-south direction, and this angle here is called the angle of dip. And the angle of dip depends on the where is your north, where is your south. That depends on the place where you are. Make sure it is facing the north and south before you hammer. Now, the moment you make sure that the angle of dip is actually the angle that you want, such that the magnet is facing north-south, now you can hammer so many times. After hammering so many times, you are trying to align the dipoles in here. So the dipoles in here will be aligned, and at the end of the day, all those magnets or all those dipoles are going to be saturated, or they are going to be rearranged until no further arrangement that is going to happen, and therefore that steel bar will have been magnetized. Now, the last method that we are going to discuss here is electrical method. Now, we can also magnetize a given material using electrical method. Now, to magnetize it, we have to use a circuit here. This is a DC current supply. DC current supply, and we have a solenoid here, a solenoid. Then we have a bar that we want to magnetize. And how do you do it? Now, already this magnetic field is going to go around, or this electric field, let's call it electric field first, because electric field is going to induce, or is going to cause the magnetic field to be introduced in our bar here. And therefore, this current here, as it moves around here, it will induce a magnetic field to the bar here. And the main problem will be, how are you going to know the north, how are you going to know the south of the magnetic field that has been produced? And therefore, this material is going to, the dipoles are going to be arranged towards one direction. At the end of the day, it's going to be magnetized. So how do you know the polarities of the bar that you have already magnetized? Now, for us to do that, we use the clock rule and the right hand grip rule. Now, the two rules are going to help us to be able to understand how to state the polarities of our bar. Now, the clock rule states that if you face the current, if you face the coil, and whatever you can see, the end of that pole is the south, because you see, for our current, we are having the clockwise direction. I mean, because I can see current is moving towards this direction. This is the clockwise direction, and therefore this end is going to be the south. So the end of such magnet is a south, because current is moving towards the, or in the clockwise direction. If it is in anti-clockwise direction, that end is going to be a north. Therefore, the end of this is a north, and this is a south. This is a south, and this is a north. Now, the hand grip rule states that if you grip this solenoid in such a way that all your fingers are facing towards the direction of current. For example, the direction of current is this one, the direction of current. So that means the thumb is going to point in a given direction. Now that direction is the north. So as you can see here, if I grip this one, this direction is going to be the north, and therefore this is north, and the other side is good. The other side is going to be definitely a south. Now that is how we magnetize materials: the induction method, single stroking, double stroking, hammering, and electrical method. So we can now look at how to demagnetize magnets. Now, just like magnetization, we can also demagnetize magnets. Now, the first way to do that is hammering and heating. Now, it turns out that if you hit a magnet, you're going to distort the orientation of the dipoles, and therefore, the moment you distort the orientation, the material has become unmagnetized, or demagnetized for that matter. Now also, hammering can also demagnetize the magnet. Now for you to demagnetize a magnet or a magnetic material using hammering, then you're going to do the opposite of magnetizing. Now during magnetizing, you are orienting, or you are positioning the magnetic material in the north-south direction, so that we can hammer. Now in this case, you're going to change the hammering such that the magnetic material is facing the east-west direction, the opposite direction as it was facing during magnetization. And if it faces the east-west direction, and then you hammer severally, you are going to distort the orientation of the dipoles, and therefore, at the end of the day, the magnetic material will have been demagnetized. Now, also, we can talk about electrical method. So, as you demagnetize a material using electrical method, you're going to have an AC supply and a circuit here. Now, regardless of the direction, but the moment you place the direction of the bar to face east-west direction, and then you induce the current to this solenoid. When the magnetic material is inside here, it's going to be demagnetized. Now, how do you know that a material has been demagnetized or not? For you to make sure that the material has been demagnetized, you're going to suspend the material on air using a string, the way we explained in our previous video, and you distort it, or you move it and leave it to rest. If it rests in the east-west direction, then it means the material will have been demagnetized. Now also, we can talk about storage of magnets. Now, I went to the office where we store magnets in the laboratory, and I noticed most of the magnets have lost the strength of magnetizing and demagnetizing. The reason is because they are not well kept. So if you want your magnets to retain the magnetic field strength, then you have to store them. So how do you store them? For you to store the magnets, we use what we call keepers. So this is a keeper, and also this is a keeper. A keeper or keepers are made of soft magnetic materials, and of course we said soft magnetic materials are easy to be magnetized, and demagnetize at the same time. So these keepers are going to hold the magnet in position. We have our piece of wood between the magnets, and then the magnets have to be in such a way that they are opposite polarities. So if these are two magnets, this is north, south, and then this is going to be an opposite polarity of north and the south. Now, if you have these as ions, soft ions, uh, this is going to be therefore magnetized to be a north, and this is going to be magnetized to be a south, north, and a south here. And at the end of the day, the keepers are going to keep the magnets in position, and therefore the dipoles of those magnets might not be distorted. The orientation is going to remain or in position. So the dipoles are going to be maintained. So that they are not demagnetized. The moment you leave them without storing them, depending on the direction where they are put, they could be east-west direction, which is high. We have a high chance of rearranging the dipoles. At the end of the day, they are going to be demagnetized. Now, we can finish by looking at the applications of magnets. Now, we have loudspeakers now and microphones. This is the main application of microphone or the magnetism or magnet. Now, in loudspeakers, these are, so in loudspeakers, we have the magnetic field interacting with the electric field to produce sound. So if you have a magnetic field and the electric field interacting and moving at a very high speed, they are going to produce sound. And so that is the main application of the magnetic field, that the magnetic field and electric field intersecting at a given rate, and they produce some sound. And also the computer hard disk. So the head of a computer hard disk is made of magnetic materials. Now the data here, or the data in a computer, is going to be retrieved from in a computer or to the computer using the magnetic field. So the hard disk contains strips which are magnetized, and the data move through those strips using the magnetic force. Now also we have application of these magnetic or magnets in medicine. Sometimes during surgery, the doctors might forget or might misplace the scalpels or those magnetic materials in there, and they can use the magnets to retrieve those scalpels or any material that they might have left in there. So in medicine, they really apply magnets to do such things. We have sorting. So if you have a mixture of, say, iron and non-magnetic material, like, say, maize or beans, you want to separate them, then you can use a magnet to sort out. And also magnetic screwdrivers. So you have seen a magnetic screwdriver. Now screws are made of steel, and if you want to remove them or to get them from somewhere and fix them somewhere, then you're going to use the magnetic screwdrivers. So that's all about magnetism, and we are going to explain more about the relationship between electricity and magnetism in our preceding videos. But that's all about magnetism as a topic. So we are going to attach questions at the end of these videos, because our viewers have requested that by the end of each topic we provide questions, and so that they can also practice using those questions. So at the end of this video we are going to attach questions involving magnetism, and also if you want the answers for those questions, then you can also comment down there so that we can provide the solutions if needed. Thank you for watching. Remember to share this video, subscribe, and also like.